Okay, so it is a great pleasure to have here today Torben Krüger, who has a joint position in Erlangen and Copenhagen, and he's going to talk about merging singularity in the normal matrix model.
Okay, thank you very much for the introduction and also for inviting me to this nice seminar. So I'll talk to you about recent work together with two colleagues. I hope you pointer. So seeing your University of Florida, and he is now position at Great Bay University in China. And the topic of the talk is, as you can see, merging singularity in the normal matrix model. Let's see. Okay, so before I start explaining the exact model to consider, I will give a very big picture overview over the general setup. I will very quickly specialize it to special cases, but first give you some context. So what we look at is a planar Coulomb gas as a general model. So that's a logarithmically interacting particle system in 2 dimensions. So we have n particles, n is the number of particles, which we will take very large at the end. And then we have a logarithmic interaction and confining potential, external potential. So the system as a function of individual positions of the particles, interaction, this log term, then some constant, also make dependent on n, and then the confining potential here acting on the individual particles. And then we'll consider the associated through this Hamiltonian, so just this measure. And you can already see, of course, that the scaling of the interaction in this model is invariant under rescaling the sum of the system. So if you want the whole system to be confined, let's say, to a compact set, one neighborhood of 0, then you should take an appropriate scaling for the external potential, and the correct scaling is so that both of these terms are roughly of the same size as the particle positions are of order 1. And since this is an n squared sum and this is an n sum, you need something of order n here, and then the overall constant is just absorbed into the v, so you can just choose this constant to be little n. So in the special case, when beta is equal to 2, which is the case that I will always talk about in the following, this is equivalent to looking at eigenvalues of a so-called normal random matrix model. So you get the same Gibbs measure if you consider random matrices restricted to normal matrices, so only on normal matrices, and then you have some density with respect to the measure on that manifold, which is just e to the minus n, and then the trace of the potential will end up giving you the same Gibbs measure. So you can exponentiate here, and then you'll end up also with this log term, but then it's as at the special temperature equal to 2, inverse temperature beta equal to 2. And if you choose, for example, the external potential, just the harmonic potential, just d squared, then you end up with the so-called Ginibre ensemble, and that's the same distribution as the eigenvalue distribution of a random matrix with just IID Gaussian entries. And in the limit as n tends to infinity, this particle configuration will end up being uniform on the disk of radius 1 in the complex plane in this particular case. And here you can already see some general feature of this kind of model, which is also true for more general potentials. First, you will have typically a compact support. Then there will be some density, which is positive, but then you will have typically a sharp drop of the density to 0 at an edge. So like here, because the limiting distribution is uniform, sharp drop at the edge. The typical eigenvalue spacing or particle spacing in the complex plane is, of course, 1 over square n, since we have n particles and they're pretty uniformly distributed. And also you see, because the density drops to 0 rapidly at the edge, the typical particle spacing is also 1 over square root of n at the edge. So there's no difference, which is in contrast to one-dimensional models where typically the particle density will decay at the edges. So you have this feature that you form some which are called droplets. The particle density is positive with this sharp drop at the edge. And I will give you some heuristics from potential theory to explain that this is also true in more general cases. So if you have this particle system, then you have the empirical measure of the particles, and this is supposed to now converge to some density rho in the limit as n tends to infinity. And then, of course, the Hamiltonian, if you probably normalize it, if you remember, it was sum over logarithmic interaction. If you just normalize it by 1 over n squared, then the Hamiltonian will approximately be this kind of log interaction, and then this density integrated against the external potential. And of course, this is also, can also be made rigorous. So if you want to know what will be this rho, then you should actually just minimize this kind of function. And if you do that, then just means that you will differentiate with this rho, and then the Euler-Lagrange system will just be the equation here. Constant L, that's the Lagrange multiplier, because of course you have to minimize properties and an inequality over the whole equality is positive, so part of the rho. And from that equation, you can already see that it's easy to get because you can just take the Laplace shift of both sides. Then on this side, and end up with the Laplace v, because the log is the Green's function of the Laplace, and you see that the density is actually just Laplace v up to some constant. So that means that if you want to know the rho, given the v in the setup, the only thing you have to do is determine where's the port of the rho. You have to determine what the boundary of this, because otherwise, it's Laplace v inside. And of course, that also means that if you have a strictly convex external potential, then the rho is always strictly positive and maybe bounded away from 0. And so that explains the sharp drop at the edge. So you always see the edge here. So now I will specialize a moment also to where we have a potential only something which plus so in this case sum over external charges. So we have now a harmonic potential, and then we add some external charges ci at positions ai. This gives this log, and in this case, of course, the harmonic potential, if you take the Laplace of that, it will just, then this part will be nothing, because the particle, if it's placed somewhere, it repels the density. So the density is certainly not positive at the charge. And then away from the charge, this of course has Laplace equal to 0. So that explains that in this case, the density is actually constant on the support, this density rho, and then the support of this density is called the droplet, and it's really true that the density is everywhere constant on the droplet. And of course, by inserting external charges, you can create all kinds of shapes. It still happen that these form these type of droplets. So for example, you can also create shape of several droplets and gap in the middle, and we will consider then where these two droplets are to meet in the middle. Okay, so briefly, I will mention the contrast to one-dimensional models. where much more is known than in the two-dimensional setup. So you can also consider the same completely analogous setup for one-dimensional cases. In this case, you can, for example, look at random matrices that are self-adjoint with this kind of Gibbs factor in front of the measure. That's also, that will lead to this this Gibbs measure for the positions lambda r of the eigenvalues. So a particle system of the same at the same inverse temperature. The only difference is that now they're confined to the real line because eigenvalues of Hermitian randomness. And in this situation, it's actually quite well understood how the density can behave. In this case, you need some assumptions on potential. You need sufficient growth infinity so that the whole thing remains confined. And also, let's say it's analytic in this case. What you will get is that the rho is an analytic function, and then the density can approach zero is in two different types. Either inside the support of the density, it can approach zero, and then it approaches zero in this kind of fashion that there can be some low minimum of the density where it touches zero, and that the behaviors of the distance to this singularity point to the 2K, or at the edges. The typical situation is what you would get, for example, in the semicircle law for the Gaussian unitary ensemble, where you just have square root singularity at the edge. This would be the case k equal to 1, but you can also get higher order vanishing singularity at the edges, and this is also described here. And I mean, by paper by Kirchbauer and Mecken, they classify this hierarchy of singularities that you can get in a one-dimensional model. So we will now ask a question. So here you can see the two cases. So this is the one-dimensional case where you have some density. Here there are these square roots, and then this is the two-dimensional model, in this case just the Ginibre ensemble, and the wiggling of these particles should indicate that they are still random, and this is the typical fluctuation of the particles. So you can see that in the two-dimensional models, it's harder to control the particles because they can move around freely in this involved area, while in the one-dimensional situation, they are confined by the neighbors, so they cannot move much. And then what we really want to know here, or what I want to discuss, is how do particles look like when you and consider only a very small zoomed in area where you can see only finitely many of them. So what we want to know is the k-point correlation function for this kind of system. So we'll integrate out all but k of the particle positions, and then we'll end up with the marginal distribution of only k particles when we zoom in. So, and of course you have to zoom in one-dimensional case, you would have to zoom in on the 1/n scale where the particles are spaced, and here you have to zoom in on the 1/square root of n scale. So the d is equal to 1 or 2, actually. Yes, d equal to 1 or 2, so square root 1 it's just no square root, and otherwise it's a square root and d equal to 2. So what you would really like to consider is the k-point correlation function at some point z0 somewhere in the spectrum or in the particle system, and then scaled correctly to the typical particle spacing scale. Then you want to stand into, and you want to know what comes out of that, and that the snapshot of this kind of statistical picture of the particle positions. And what you expect is to see some determinant point process. I'm considering the case beta equal to 2 here, then you typically see a determinant point process depending on these rescaled positions. And we hope that this is a universal result. So it should come out in all these cases basically the same, depending on where you are in the picture. Now, in the one-dimensional case, this is fairly well understood. So for the beta ensemble, which is the ensemble that's the one-dimensional analog of this Gibbs measure, the case beta equal to been done already for quite a while. The succession of doing as is always the same. First, this is beta equal to 2, because that's the easiest. And then beta equal to 1 and 4, because these are the other classical cases where there's still a random matrix associated to this system. And then afterwards, the hardest case is general beta. As you can see, for the bulk, so inside the spectrum, where the density is positive, showing that this kind of holds, that you can get the local correlation function has been done for beta equal to 2, then for 1 and 4, and later also for arbitrary beta. And in this case, the universal kernel is a so-called sine kernel that comes out of this. Then in the case of the edge, and in this case, in the one-dimensional case, that's the square root edge at kind of edge dimensionalization. The same thing has also been shown for beta equal to 1, then for the classical betas, and then for arbitrary beta. And here, the typical spacing scale at the edge is n to the minus 2/3, so you have to correctly scale because the density tends to 0 at the edge. And then if you take the limit, you get this Airy kernel, this is the Airy function. And then you can also analyze for in the middle of the density, which the simplest kind of singularity is a singularity of quadratic vanishing density. So this has been done first by Blair and Itz in 1999. For this special potential, if you look at that kind of potential, there's a parameter t here, and you can tune the t, then the density in this case, these three pictures, depending on the value of t. So you can either have a connected component as the support or the droplet, and you can have two connected components. And if you have a critical case, then you have a vanishing density in the middle. And then the question is, what's the behavior at this vanishing density? And here the typical spacing of the particle distances is n to the minus 1/3. And if you take the limit here, then you end up with this kind of kernel. I will not at the moment explain the functions psi1 and psi2, but I will introduce them later. They will appear later. Notice that there's already psi here, which is just an explicit function, psi1 and psi2. I will define them later. Okay. Then in the two-dimensional model, the situation is somewhat worse, quite a bit worse. So we don't understand nearly as much in the two-dimensional case. First, I will basically only talk about results for beta equal to 2, because otherwise there's not much known about universality. In the case beta equal to 2, we still have, even for finite energy determinant, a point process described in terms of determined kernels, and then you can just take the limit n to infinity and try to figure out what the kernel converges to. And so for the bulk of a model, and this is all with sufficient regularity on the external, typically analytic exponential. So this paper by Yasin, Hidman, and Makarov, they prove that if you look at some position which is somewhere completely inside the spectrum, where the t is positive, away from the edges, then if you take this kernel and this point, you rescale to the typical spacing, the limit, and you get the same answer that you would get in the explicit calculation in the Ginibre ensemble, where you can explicitly compute this kernel. And then for edges, this has also been proven. Yeah, of course, there's a direction, right? Because in some direction you're moving outside of the droplet. So what you can see is that there's some angle that basically tells you in which direction you're moving outside of of the droplet. And then if you rescale at a z0, which is at the edge of the droplet, and you rescale with the same scaling as in the bulk, 1 over square root of n, so that remains exactly the same in the bulk, then you end up with this kind of kernel, the Faddeev kernel, which looks like the Ginibre kernel, and then this has this function factor here, which is the integral over the Gaussian distribution. And you can also see that, of course, if you move inside the spectrum, then this error function will just tend to 2, and then you'll have the Ginibre kernel back. And if you go outside of the droplet, then it will just go to 0. For general beta, actually, none of this is known, but there are some results on the partition. I will just briefly comment that there's a lot of recent work in the general beta case, mostly by these two groups, and they figured out the main contribution to the partition function, and also some fluctuation. So some central limit theorem and even some mesoscopic central limit theorem known, but analogous results for general beta are not known. So now we'll go to a very special case. And the reason for that is that we want to understand the other possibilities. So now we have here the bulk universality and the edge universality, but now we would like to understand also some other singularities. And for that, we start with the easiest model where such a singularity appears. And the first thing we want to do is just determine what the answer is. So this is far away from universality. This is just computing the answer in one model. So it's just to see what you should expect. So what we will now do is we will restrict to a very special model, which is the simplest model where the first type of singularity occurs. And that's a model where you have a harmonic potential and then one external charge, A, which is placed somewhere here, or here, or here in these pictures. And then there's a parameter T here that we can tune. And if T is smaller than some critical value, it doesn't really matter what the critical value is, then you'll have just one, the droplet is just one single simply connected area. And if you have the T larger than the critical value, then you'll have the droplet enclosing the external charge where you have no density. So the droplet is the gray piece in the picture. And then there's also a critical regime where these two things exactly touch here at this critical point. And this is exactly the situation where singularity of one of the types occurs. So this is the type of singularity that we're talking about. And you get the same type of singularity if you would have two droplets that touch each other in the middle. I mean, that also creates some quadratic looking singularity. But in that case, it's harder to do this computation, which I'm not showing. Okay. Now,
can I ask a question? So what are these blue dots mean? All right.
Yeah, okay. So there's a singularity on the, so this is the Sego curve associated to this model. This is not so relevant now for what I'm talking about. Okay. It will be more relevant for the proof later.
Okay,
so there's a Sego curve associated to this model, and this is basically a critical point on the Sego curve. There's a cusp here at this point, and then there's a critical situation here, and here it splits into two, and this is the
okay, so I should have better asked, where is the charge? Where is A?
The charge, yeah, I should have actually put the charge explicitly. So the charge is basically in the middle of this Y. And here it's just to the right of the picture.
Yeah, thank you.
Yeah, the charge is missing from the picture. That's right. Okay. Thank you for the question. So the important thing is that we will look at this critical case where there's the singularity appearing. And luckily for us, my co-author and McLaughlin and Bertolla and Balotti, they already computed this picture. So the global droplet, and also they computed some strong asymptotics, the leading order for the strong asymptotics of the associated orthogonal polynomials. This will be important later, so I'll skip the details and instead talk about the results now. So what do we observe at this singularity, which is this merging singularity? So the first thing we observe, which you can already see in this picture, is that because these are two circles that touch each other, the droplet locally at this point looks like two parabolas, right? So the density is confined locally by two almost parabolas. So at least if we zoom in at the critical point, we'll see two parabolas. So if you take a mesoscopic distance from this critical point, so you'd let n tend to infinity, and then you take a mesoscopic distance, so not distance 1, but something that shrinks with n. So let's say we look at n to the tau with 1 over n to the tau, where tau is some positive number, and we shouldn't take tau too large, so because otherwise we are very close to the singularity. So in this case, the critical threshold is 1/4, so you should stay a bit away from the singularity. And if you then look at the 1-point function, that's the density, the particle density for the system, and you look at the critical point and you scale the x direction like 1 over n to the 2 tau, and the y direction like 1 over n to the tau, then what you get is you get two parabolas. If you're outside the two parabolas, you get 0. And if you're in between the two parabolas, you get some positive number, which is just the value of the density at that point. So that's not very surprising. That's just somehow zooming in the density. And then you can push this a bit further, and this is somehow where it gets interesting. So if your tau is exactly 1/4, so then you're quite close to the singularity already. You're on the scale n to the 1/4 in the y direction, but you are in the x direction, you are n to the -1/2 away from the critical point. Then you get a non-trivial profile. So that means that there's a characteristic length scale where the density lives, and it lives on this length scale n to the -1/4 away from the singularity. It moves from 0 to the value of the Bach, so from 0 to 1 essentially, or 1 over pi t c. So that's the Bach value. So there's a characteristic length scale of the density, which is n to the -1/4. Okay, so that's the first result about the global density. You can see the corresponding picture. So if I look at this critical point, and now I took a very small neighborhood of it on the scale n to the -1/4 in this direction and n to the -1/2 in this direction, then I will see this profile. This is how the density looks like locally. Okay. Now you can do a bit better if you want to know, for example, how the density moves from the bulk value down to 0 at this edge when you're in a mesoscopic distance. So again, tau is between 0 and 1/4 here, and you fix now a point which lies exactly on one of the two parabolas. These are the two parabolas that define the edge. So this is just an edge point, and this is another edge point. And then if you rescale on the 1 over square root of n scale, which is the typical particle spacing scale, then you can even recover the error function behavior here, which is the same behavior that you would get if you would rescale at the Ginibre ensemble at an edge point. And then you would ask the question of how the density looks like locally. So and this is somehow the difference also between the Ginibre and this ensemble is that at a typical edge point, the spacing scale of the particles is the same characteristic length scale as the density, 1 over square root of n. But that's not the case here. Here, the density has the typical length scale n to the minus 1/4 in the y direction, in the x direction n to the minus 1/2. But the typical particle spacing scale is different. So the situation looks like this. In this direction, we have n to the minus 1/4, and in this direction, n to the minus 1/2. And this is this profile, this non-trivial density profile. Now we can zoom in further. And of course, if you zoom in further, I'm not zooming this direction. This is still n to the minus 1/2, but I'm zooming in this direction. So I'm now going closer to the singularity than n to the minus 1/4. If I do that, then of course, you cannot see these parabolas anymore that you can somehow see in this picture appear, because then everything will be straight. You zoomed in too much. So everything will be basically confined to some strip. But the particles are still very clustered in the y direction because they are very close to each other in the y direction, too close actually to resolve them. So if you want to see them, especially in the middle of the singularity, then you have to zoom in much further to the scale n to the minus 1/3, and then you will see that the typical distance of the particles is order 1. So if you zoom in this way, this anisotropic way, then in all directions, the typical spacing scale is 1. Okay. So then you can see a non-trivial particle system, and then you can ask the question about the correlation kernel of that particle system. And that's the next result I want to talk about. So in order to explain the statistical behavior of this particle system, I have to introduce this psi function, which I mentioned earlier. So this will be how the psi function is defined. It doesn't really matter so much what the exact definition is. It's just a special function. There are two functions, psi1 and psi2, that form a two-vector psi. That depends on two parameters, xi, which is a complex number, and s, which is a real number. And this psi vector satisfies two coupled differential equations that are written up here. They have some matrix here multiplying this psi vector and some other matrix here multiplying this psi vector. And then they're uniquely, that's an ODE system. They are defined by the asymptotic behavior at infinity. So as the xi moves along the imaginary axis, you get some asymptotic behavior that defines you which solution of this ODE you should consider. And the function q that comes up in this equation, that's a solution to the so-called Painleve II equation, which is this ODE written up here as a second order ODE, with this kind of asymptotic behavior that uniquely defines you the solution. So it doesn't really matter so much what it is. It's just an explicit function, which is called psi1, and there's another one which is called psi2. Okay, so now given these explicit functions, you can define correlation kernel, which is in the x direction just a Gaussian decay, and in the y direction it's this kind of what's called the Painleve II kernel. So this is defined by these two functions, psi1 and psi2, with this parameter s. And now what we look at is exactly this very tiny neighborhood of the singularity with this anisotropic scaling. So in the x direction, n to the 1/2, n to the minus 1/2, and in the y direction, n to the minus 1/3. And then we consider, this is the critical point, and then we also consider this parameter t, which came up in the Gibbs measure, dividing the factor n in front of the potential. We can also make it n-dependent. You can also set it equal to the critical value all the time. In that case, this s, which comes up in this equation, is just 0. So that's fine. But you can also allow this gap to open a little bit. You just have you have to open it just a tiny bit. So it's really, this thing is a family of kernels. It's not just one kernel, and this family depends on this lower order contribution to this scaling t which can be of the order n to the minus 2/3. So if you take the t minus the critical value and you multiply by n to the 2/3 and you define that as s, if the limit exists, then this s will also end up in this kernel. So what you see is, if you look at the correlation kernel in this anisotropic scaling, then as n tends to infinity, it converges to this specific kernel here. There's a prefactor here, which really is irrelevant. It's called a cocycle. It's something that is the form e to the I and something divided by e to the I, the same thing with the other variable. And this kind of cocycle will drop out if you compute from this kernel correlation function. So if you compute the correlation function, which is the determinant of this kind of correlation kernel, then this cocycle will drop out of this computation. So it's irrelevant for the physics of the particles, if you like. It's just something which comes up in the computation. Okay. So this shows you that you can compute also the correlation kernel very close to the singularity. And now the interesting thing is that the particle spacing scale is the typical particle spacing scale in the y direction is n to the minus 1/3, but the density lives on the scale n to the minus 1/4. So there's actually a rich scaling behavior also in between these two. So what you can do now is you can, I should have really drawn this rotated by 90 degrees, because this is supposed to be the y direction, not the x direction. So think of this one as being rotated 90 degrees. Then there's the critical point. And now you can be also a distance 1/n to the tau away from the critical point, where tau is between 1/3 and 1/4. So remember, 1/4 is the spacing scale of the density. So now we're in between these two. And in the x direction, I'm still taking the 1/√n scaling. But in the y direction, so I'm fixing now a point here somewhere in this distance from the critical point. But then at that point, I'm also asking a question about the spacing scale. And the typical spacing scale around such a point will be 1/n to the 1 minus 2 tau. So there's another scaling here. So this Bn is this point, which I fix in the distance n to the 1/n to the tau away from the critical point. And then I'm around that point in the x direction, I'm choosing a distance 1/√n. And in the y direction, I'm choosing 1/n to the 1 minus 2 tau as the spacing distance. And then I will see also the sine kernel appear in this situation. So in this situation, in this distance, you will have the sine kernel. You can think of it this way, that the particle system is in such a way that it's pretty in the x direction, it's confined to 1/√n distance, but in the y direction, it has a wider spacing scale. So it's effectively one-dimensional. That's why the sine kernel comes up here. And then you can also go further and go to the scale on which the density lives. So now I'm going further. I'm going further away from this critical point to 1/n to the tau, with tau being exactly 1/4. That's the critical scaling for the density. And then at that point, I'm now asking the typical spacing scale at that point, and that will be 1/√n in both the x and the y direction. So now I'm entering the regime where it's really a two-dimensional system. So it's not effectively one-dimensional anymore. It's really two-dimensional. So if I do that, then I end up with this kind of kernel. And that corresponds to a kernel which is basically a Coulomb gas confined to a strip. So it's like having a Coulomb gas in a harmonic potential that grows only in one direction. So it's confining a Coulomb gas to a strip. So this is really a two-dimensional model. This kernel has already appeared in some earlier work where it was predicted that something like that happens at these type of singularities. So this paper proved that the correlation function has to satisfy some equation, and it proved also that the only translation invariant solution in one direction to that equation has to be this one. Okay, and here you can explicitly also see this correlation function come up. Okay, so so this is the kind of rich behavior in this situation, and now you can also go further away from the singularity, and then it starts to become the correlation, and the behavior starts to become the one that you would also predict from just looking at the Ginibre ensemble. So now if you go to a mesoscopic distance, even further away from the singularity, then you have basically three choices. Either you chose a point which is outside of the spectrum, that's basically away from the two confining parabolas. If you do that, then you get 0, of course, nothing happens there. And if you choose something in between the two confining parabolas, you get the Ginibre bulk kernel. And if you choose something exactly at the edge point of the parabolas, you get the Ginibre edge kernel. These are these three cases. And the typical, so you just choose a point which is a mesoscopic distance from the singularity, then you get these three cases on the typical spacing scale, 1 over square root of n. And we have this restriction here that tau is only up to 1/6. Between 1/6 and 0, we expect exactly the same behavior, but then you will start to see the curvature of the circle. I mean, the circle isn't really a parabola, it's just locally a parabola. So then you have to do more corrections, and we didn't quite do that here in this paper, because also we expect the answer to be basically the same in that case, but it would have been doable. It's just a matter of doing higher order corrections to the computation. Okay. So now, I don't know how much time I have left.
Until 4, so 20 minutes.
Okay, but probably there are questions also. So
yes, so okay.
I will try to to not take the whole time. So I will give you some rough idea of the proof. So the proof is based basically on an explicit computation of the kernel in all these cases. So we use the determinantal point process structure of the model. You write the endpoint correlation function as the determinant of the correlation kernel, which is expressed in terms of orthogonal polynomials. The orthogonal polynomials are defined by taking the expectation value of these kind of products, z minus zi, where the zi is the ith particle, and the expectation is with respect to this measure rho defined by rho n. So this is the density. So this is the expectation with respect to the Gibbs measure. And then these orthogonal polynomials satisfy some orthogonality condition with respect to this measure that has the confining potential in here. And then, of course, the k-point marginal distribution will again be just the determinant over this kernel with only k entries. So that's this typical setup for determinant point processes. And then we use an identity which is analogous to the Christoffel-Dabou identity in one dimension. So in one dimension, if you have orthogonal polynomials, there's always this Christoffel-Dabou identity. In two dimensions, this is quite a bit harder, but in this work here, my two co-authors together with Björn have derived for this very specific case when there's one external charge, a Christoffel-Dabou identity. So let me recall that the main problem if one wants to compute the asymptotics of this kernel is that there's a huge sum of orthogonal polynomials here. And not only do you have to understand the asymptotics of the orthogonal polynomials, these are these PNs, they're just multiplied by some factor here to generate these extra functions psi. So you have to understand how these orthogonal polynomials behave as n tends to infinity, but you also have to sum n of them. And that's of course not very pleasant. So then the question is, how do you do that? And one way out is if you have to Christoffel-Dabou formula, then you can reduce this sum to just the asymptotic behavior of a few of these orthogonal polynomials. And in this particular case, that's possible. So there is a Christopher-Darboux formula for this setup, which is expressed in terms of these essentially this orthogonal polynomials multiplied by some prefactor, and it's for the derivative of some of this kernel essentially. So there are some modifications, as you can see, just to make the formulas fit on the slide. But essentially, you can think of the psi as being the orthogonal polynomial, and this k, even the script k, is the same as the kernel. There's just some trivial prefactors. And what this says is that the derivative of this kernel is expressible in terms of finitely many of these psi's. So in this formula, there's only a psi n minus 1, and psi n plus 1, but no big sum anymore. So there's no sum like that. Okay. And these hns, these are the normalization constants from the orthogonality condition. So these are just some independent numbers, but also they depend, I mean, this depends only on finitely many of them, just the hn minus 1 and hn plus 1. Okay, and then you have to compute all of them, and the limit n tends to infinity. And the way this is done is by formulating a so-called Riemann-Hilbert problem. So what you do is you write the orthogonal polynomial into some 2x2 matrix together with some other orthogonal polynomial that is determined by some external potential, some potential function. It's explicitly written here. Also, it doesn't really matter so much what it is, but there's a formula where you can write orthogonal polynomial together with some other polynomial that's determined also by some orthogonality condition, and together with this kind of integral into a 2x2 matrix. And then what you can see is that this 2x2 matrix satisfies a so-called Riemann-Hilbert problem. So it satisfies some equation on the complex plane. So Z is a complex number. And so what this says is that at infinity, this 2x2 matrix has some asymptotic behavior. Otherwise, it's a holomorphic function in Z. And then there's some curve called gamma in this case. This is a curve that's supposed to go around. This is just one closed curve that encloses both 0 and the position of the external charge A. Otherwise, it's arbitrary. And then this 2x2 matrix satisfies this problem where y plus is the limit of the y if you go to the curve from above, from the outside, and y minus is going from the inside, and then at the curve there's a jump. So at the curve, the function is everywhere holomorphic, but it's discontinuous at this curve, and the jump is given by this multiplicative condition. And it involves this thing. This is called the Riemann-Hilbert problem, and this has to be solved to do that. And it's solved. There's a machinery to solve it. This is some nonlinear steepest descent method. So you first do some global transformations called the G-function transformation. Then you move this to a different type of Riemann-Hilbert problem, where now this Szego curve from your question, Hal, at an earlier stage of the talk appears. So this is this B. So this is the Szego curve. So there's a jump condition after this G function transformation. You can make this into a new Riemann-Hilbert problem where there's a constant jump condition along the Szego curve. There's some asymptotic behavior at infinity, and then there's this kind of condition at some curves that basically are created out of the gamma. There are some steepest descent curves close to the critical point. And the important thing is that this is basically everywhere 0, because this is some phase, or it's some exponential, but this phi on this curve here is always smaller or equal than 0. If you are sufficiently away from the critical point. So somehow away from the critical point, this is basically 0. And then this problem is explicitly solvable. I mean, it's very easy. The jump conditions are all constant, and you can just solve it. But very close to the critical point, you have to watch out, because there this number when the phi starts to become get close to 0, and then you have to be careful. And then you have some machinery where this is this other transformation. You have to introduce some local coordinates that resolves the 0 structure of the phi, and this 0 structure of the phi is given by some cubic equation. So you introduce some local coordinate xi that solves some cubic equation, and then you transform the problem by introducing this local coordinate in some other Riemann-Hilbert problem, which is only valid locally, very close to this singularity, and that has this kind of structure. And here you can already see the psi appearing. So somehow this already looks very suspiciously like the problem, the ODE problem that I introduced earlier. This has something to do with that. This also you can somehow see is a quite explicit problem, and this is sort of solvable. This is the model problem for this situation, and you can solve this problem in terms of the psi that I introduced earlier. So there's this ODE that one can solve, and if you have the solution to this ODE, then you can also solve this Riemann-Hilbert problem by this relation. Yeah, so this is how the psi comes in. Okay. So I will not really go into details on that, I think. So this is called the Painleve II Riemann-Hilbert problem, and there's an explicit solution in terms of this ODE that I introduced earlier. And then the whole thing has to be patched together. So essentially what you can now do, I'm going back, you can solve this local problem, and then when you have solved the local problem, and you have done this coordinate transformation, the G function transformation is basically the transformation that takes care of the global structure of the problem, the density, the droplet, and so on. And then you can move back and get back the original Y, and then you can see how the orthogonal polynomials behave. And somehow the finesse of this problem is that you have to do it to quite high order. So in the previous paper that I cited, they determined basically the leading order for the orthogonal polynomials. But what you have to do now is you have to express these orthogonal polynomials also to lower order. So you have to do some lower order expansion in n, and then you get some behavior of this orthogonal polynomial in terms of these functions psi that are the solution to this ODE problem, and then some coefficients. And these coefficients are have to be determined to the order 1 over n to the 1/3, 1 over n to the 2/3, and then some error term with some coefficients that explicitly depend on this function q, some solution to the ODE that I talked about earlier. And once you've understood this p to this degree, then you can plug everything into the Christoffel-Darboux formula, and you can basically compute the kernel. Okay. So this is my talk. Now I will tell you a few open problems that have to do with this topic, and then I'm happy to answer also questions. So one certainly open question is to prove some type of universality result. So this was basically just computing the answer. Now it's a quite rich scaling behavior, but we expect the scaling behavior to be universal. So in principle, one should be able to check that with a different external potential and the same singularity, you get the same behavior. More generally, there should be a connection between the hierarchy of kernels and scaling behaviors in this two-dimensional model corresponding to the hierarchy of one-dimensional singularities. And this is also connected to this KdV hierarchy of some partial differential equations, which is suggested in some physics paper in PRL. So it will be interesting to understand a bit better this connection. Then, of course, well, this only works for beta equal to 2, so it would be interesting to do in other beta. But of course, this is much harder because then the determinant of structure isn't there anymore. And then also what would be interesting is to understand a dynamic situation. So this kind of merging singularity, of course, can also appear if you look at the Coulomb gas with some dynamics, basically like Dyson bond motion. So particles can wiggle and then have this log interaction, and then they will also form this kind of merging singularity. And then one could also ask the question of what happens to the universality classes at these singularities. Okay, very good. Then thank you very much for your attention, and I'm happy to answer questions.
So thank you very much. Are there, okay, you are free to unmute yourself and ask questions. Otherwise, I will start. So what you're doing, you are using in a very, very strong way the fact that you have a determinantal point process, right?
Mm-hmm. Yes.
So then is it always that it's a determinantal point process, or you're assuming that if it's not, you would like to use universality to prove that it's still the same, or?
I mean, in a way, all the results, I mean, at the beginning, I told you the results in 2 dimensions that are known, and they all use the determinantal point processes. They are always for beta equal to 2. I mean, there are some results for beta different from 2, but they are not universality results about local correlation functions. They are central limit theorems, which are, of course, on a mesoscopic scale. They are not on this particle level spacing scale. So I don't think there's anything really known about the universality on the spacing scale of these models if beta is not 2, because exactly what you say, how do we compute the kernel in that case? It's a very hard problem.
Here you're really using the fact that you can go to orthogonal polynomials, and then you study in a very detailed way these the asymptotics of the orthogonal polynomials, right?
Yes, yeah, that's right. I mean, it's a very difficult problem to understand what happens if we don't. I mean, because then you don't have a kernel to start with. I mean, basically you don't have anything to start with. That you cannot. There's nothing you can understand asymptotically. Of course, you could try to do some more PDE approach, Dyson bond motion type of approach to do that. But that's much harder problem. Even it would be very hard to compute in some simplest model. Let's say harmonic potential. The answer. Right. Okay. I mean, even because how do you compute the answer? I mean, even to compute the answer in Ginibre case for the Gaussian harmonic potential case, you somehow use machinery. Right? Yeah. Okay.
I see. And I had actually another question that was more on the technical part. So you have all these limits for different tau, so different scaling, different distances.
Yeah.
And then you have windows. And the limit, so in each window, the limit does not depend on tau, or it depends on some constants. So because in the limit, I don't see any tau, they seem to disappear.
Yes, okay, that's kind of the point, right? So the point is that it's universal. So the idea is that so there are several different regimes. There's a regime very close to the singularity where the spacing scale is the anisotropic spacing scale, and where the Painleve II appears. There's no tau here. That's the naturally smallest scale you can look at. I mean, the smallest you can, the closest you can be to the singularity. You cannot get any closer, otherwise you will not see anything. You don't see any particles anymore. And then you can move away from the singularity to a distance 1/n to the tau, and then tau is here between this very closest scale and the typical scale of the density. So here, if you like, the density still goes to 0 in this regime. The density of particles is very low in this regime. It still goes to 0 asymptotically. But of course, there are still a few particles there. They are just spaced further away, and that's why the density goes to 0. And then, of course, you have to adjust the point you expand around is in this distance from the 0, but then at that point the particles are they are much closer together than this distance from the critical point, right? I mean, how they are close together is much further than this distance. I could have maybe put this in a better picture. So this distance is much closer than that distance. Okay. So the particles are actually squeezed together much more than the distance from the critical point. So you have to look at this expansion point and then look at the spacing scale, which is the particle distance. And in this regime, essentially, the whole system is confined to a one-dimensional tube with a quite long distance in the y direction of the particle spacing. So it looks like a one-dimensional model. That's why the sine kernel comes up.
Okay.
But then it still has a decay in the x direction because there's still the thing is confined somehow. And of course, this doesn't depend on tau anymore because we scaled it correctly. So that's why the tau doesn't come up. Of course, the tau comes up in the size of the density, right? How big the density is depends on how far you are from the single. And then if you take the typical distance of the density, then you start to enter into a regime where the two-dimensional structure starts to matter. So now the particles have really a two-dimensional interaction, and this starts to, you're still very close to the singularity, so you cannot see the two parabolas yet. You're too close. So the whole system is basically like something confined to a strip. But now it's two-dimensional, so it's like a Coulomb gas in a harmonic potential. But the harmonic potential is only a one-dimensional harmonic potential. It's a confinement in one dimension. So it's like a Coulomb gas in a strip. And this has this two-dimensional model. And there, of course, the tau is fixed to be 1/4. And then if you go beyond that, then essentially you've left the interesting piece. Now you're in the regime where you can see two parabolas. And if you're in the middle between the two parabolas, this is just bulk behavior of a two-dimensional Coulomb gas, which is the Ginibre bulk behavior. And if you're at one of the two parabolas, then you're at the edge, and then you have the edge Ginibre behavior. And of course, that also... Sorry.
There is a question. Wait. There is a question in the chat.
Oh, yeah, okay.
In your proof, it seems to be the Christoffel-Darboux type identity is the one of the Crookes tools. Yes. Do you expect that there is a Christoffel-Darboux type identity for general two-dimensional determinantal Coulomb gases models with a general potential? And if not so, do you think that what is the structure to derive the Christoffel-Darboux type identity?
Yeah, that's an excellent question. So, okay. So, of course, that's another, there are two very important tools here, the determinantal structure, and actually maybe three. So the determinantal structure, the Christoffel-Darboux identity, and then related to that, otherwise this you cannot analyze it, you need to know the Riemann-Hilbert problem for that. The Christoffel-Darboux identity is also an important tool. If you cannot start with that, it's very hard to do anything. Actually, the paper that does the edge universality, the Hardeman paper that I cited at the beginning, it doesn't use really this Christoffel-Darboux identity. So you can do something, but then you have to rely on that there are some terms in this big sum which are leading or something. It's very hard to get that in general. I'm not sure. So I think that in special models that are generated by external charges, you can get these kind of identities basically all the time, but they become more and more complicated. They become really messy. But for general potential, I've not seen anything. like that. That would be great if that would be possible. So if there were Christopher Dabur identity for general potential, that will be a very good starting point to prove universality. But I don't know. There's as far as I know, there's no such thing.
Okay, many thanks. Yes, okay, I see in the chat. Other questions, or you can write them in the chat. Okay, if not, I think we can close the official part of the seminar, so we can stop the recording.